Heard the okay, there it goes. All right, hello. This is Marvin Jones, and this month's ZK call, I will be presenting the Sumcheck protocol. If you're new to the ZK space, you've probably seen the ZK protocol, the Sumcheck protocol get mentioned from time to time. And if you've been in the space a while, you certainly have heard of the Sumcheck protocol. So today we'll talk about it. The first question, for anyone new to the space, we'll always ask when it comes to any protocol is, well, how or where is the Sumcheck protocol used? Not like how does it work, but why should I care about this protocol? There's a million other protocols. Like, why is this one special? So we'll give you a few instances where this is used. First, because I like theoretical stuff, I will start with the most important to me is that it was used to show that the space of all interactive protocols is just P space. So any problems that can be solved in polynomial space using polynomial space. So those two sets of types of problems, ones that can be expressed in an interactive protocol and ones that can be solved using P space, polynomial space, those are the same. Okay, so that's cool from a theoretical standpoint, but if you're an engineer, you're like, yeah, that's fine. Who cares? Okay, fair enough. The other way that it can be used is for multilinear extensions of a vector. So if you're dealing with anything in a computer, it's often expressed as an array. And we've mentioned in other ZK calls that you may have seen, but the way that you can take an array to be used in a polynomial commitment, as we may have talked about in the past, is to create a function based on it. And that's a multilinear extension. And that will essentially kind of use Sumcheck protocol kind of in the background, at least to convince you that it's there, but certainly within the GKR protocol. So the second one's a little bit of a stretch, but more importantly, GKR protocol. And the reason that you might care about the GKR protocol is if you've, again, been in space a little bit and looked at some of the complexities, oftentimes the prover complexity is just no one pays attention to it. It's something outlandishly large and not necessarily practical. GKR was specifically designed for the practicality of it. So for the prover side. So okay. Now that we've dealt with the why you might use it or why you might care about it, what is it? Well, okay, cool. As you can imagine from just based on the name, there's a sum. Okay. Well, what we're going to deal with is a sum over an entire set of H. So we have a finite field F, and we have some set H. And if I have a v-variant polynomial, so a v-variant polynomial is just a polynomial with v variables, x1 through xv, then the goal is, can the prover convince any verifier that is restricted to only logarithmic time of this sum, where I basically plug in every combination for all my v variables of values in H, and that is sums to be some value C. So that's the objective. All right. So that's the problem we're looking at. And this problem can actually be done with a recursive algorithm, which is very nice. So cool. But again, let's take a step back, with before we get into the weeds of how this algorithm works, let's, for a moment go, okay, why would I want to even have a prover do this? Why? What does the verifier know? What does they not know? Well, the verifier in this particular instance knows a lot more than you might assume. In zero knowledge, we often talk about the verifier basically knowing nothing. But in this instance, they know what C is, they know what the set H is, but they also know the polynomial. So that's like full knowledge. Well, okay. The Sumcheck protocol, though, isn't a zero knowledge protocol itself. It's an interactive protocol. Um, so the next question is, okay, if the verifier knows all this stuff, why doesn't the verifier just compute the sum themselves? Why do I need a prover to tell me the sum? Well, as I mentioned earlier, the verifier we're assuming is computationally restricted. They can only do a logarithmic number of computations. And this sum, if I go through every combination of h for each of these variables, is going to be exponential. It's going to be the size of h raised to the v. All right. So, and feel free to interrupt if you have questions. So, but otherwise, I'll keep going. But that's why the prover is necessary in this instance, not because there's anything unknown, but we will briefly at the end of the talk mention how you can turn this into a ZK protocol. But for the purposes right this moment, everything's known. It's just computationally too expensive, and we need to outsource it. So now we're going to talk about how we do this computation. And just to kind of remind us what we're working with, I have the general formula that we want to do at the top. And each step of the protocol can kind of be thought about as the prover is going to send some univariate polynomial to the verifier, g of x. The verifier should check the degree of g with f, and it should check the evaluation of g with c. Now, you might be going, okay, well, if this is a recursive algorithm, something needs to change. And you're absolutely correct. There's going to be a lot of changing as we're going. So the value of c is going to change each time, because what's going to happen is that polynomial g of x is going to be related to a specific variable. So that degree is going to correspond to a specific variable degree in f. And that c is going to change, as we will see in a moment. All right. So the very basic step of the entire algorithm, well, the first thing we're going to do is we're going to define this g of 1. And what g of 1 is going to be is we're just going to, in our polynomial f, wherever we have x1, we're just going to leave it as a variable, and all the others we're going to substitute in with our combinations of h's. And we're going to sum over all those combinations. And that's going to give us a polynomial just in terms of x1. And if I send this polynomial to the verifier now and tell the verifier, okay, you have this polynomial, just go add every combination of h into this, then it should come back to c, because the prover handled h2 through hv with all those combinations, and now the verifier is going to handle all the combinations as just h1 essentially. So we get that, and you go, okay, this g1 matches what I expected from f. Great. So the verifier goes, okay, cool. I'm going to select a random number in my field, R1, and I'm going to compute what C1 is as G1 equal to R1. All right. So now we have fixed one of our variables at this point in time. So the verifier knows that G1 is equal to of H over the whole combination is C. We know that G1 was, if G1 was honestly constructed, we know that this is going to just be C1. So we know a good bit. And the honestly constructed portion, that refers to the prover's view of this as well, just for context. Like, the verifier has no reason to believe that any of this has been honestly done, but we're going to hope it is, and we'll see the likelihood that it wasn't. All right. So after we do this base case, then we can do this for all the intermediate steps as well. So for some ith step, I have g-ith polynomial for variable, the ith polynomial xi. And we have a bunch of these constants that we've accumulated from the verifier. So we define it the same way. And we're going to just sum over all this. Great. We're going to, again, check the degree of g of I with f. Okay, that's just looking at the degrees. And then we're going to go, okay, does my new polynomial, this should be a gi, by the way, just notice that, but does this sum for gi, does it come out to be what should have been being the ci? So we're just checking each step. We get a new ci when we select a new random variable, just like the base case. All right. So as we iterate all the way through, we kind of go from f with this value c to g1, g1 to g2 with the c1, comparing what the sums over the whole thing should be. And we get all the way down to here. But you believe that the whole, following the steps, you're like, okay, sure, if you were honest here, I believe that this evaluation should correlate, but there's, I'm just restricting, we're telescoping down. So there's nothing connecting GV back to F, at this point. Like, I know what GV should be when it's evaluated. It should be correlated essentially to R1 all the way up to RV or something. But these aren't connected. So it's not quite enough. Somehow I have to circle back. And the way we need to do that is we do an evaluation so that we can sweep back and go, okay, at this point, I had this polynomial f that was given to me. I've done this iterative step to get the CV. And what CV actually is it's this very weird evaluation of f at one point, one random point that the verifier selected at each step, R1 through RV. And that sweeps us back to an evaluation of F. So now I need to evaluate F to make sure it matches with my final evaluation. And that's kind of that missing step. So there's two ways we can do this. The verifier can evaluate F at that point. That could be expensive, depends on the polynomial F. Alternatively, we can offload this evaluation from the verifier using like an Oracle mode model and polynomial commitments. So if you have a multivariate polynomial commitment, you can go ahead and do this computation and have the prover, compute it and prove it to you. All right. So that's the two ways you can do that. All right. So let's kind of look at an example of this because, again, there's two ways you can look at it. Either you can look at it from, you're new to it and you're going, okay, that was a lot of equations. Didn't quite make perfect sense. And, or you're looking at going, okay, the equations make sense mostly, but I still need an example. So in either case, we'll have an example. The first thing we're going to say is, why am I taking P to be a lot larger than 50? And that's all that these greater than means, is that we want a prime number that's just a lot larger than 50. Why larger than 50? No theoretical purpose. It's just I don't want to do I didn't want to do any reductions on the modulus in this instance. So that's why. So anyway, the other question is possibly why 0, 1? 0, 1 for a few reasons. One, clarity of the example, because if you start adding more numbers in there, it gets convoluted. Two, well, basically everything we're going to be doing with ZK snarks are on computers. And as I mentioned earlier, multilinear extensions. So if you want to provide a binary representation of a location in your array, you would be using 0, 1. So that's why you would practically do it for the example and practically do it for engineering's sake. But this is the polynomial we're going to be considering for this example. It's a fairly nice polynomial. It's very short, which is good. And if you were to plug in every combination of 0, 1 for 3 variables, you'll hopefully come up with the sum being 3. So either I'm really consistently bad at arithmetic or it's 3. So I'm going to go with that. It's 3. And the first real step after the claim, this is a published claim that the sum is 3, and this is the polynomial. But given that, what we're going to do is we're going to have the prover fix the variable z. There's no reason to fix z instead of x first. It's personal preference. I don't remember the particular reason for that preference when I wrote this example originally. I think it was for the sake of reductions presentation, but that's just in case you're wondering why I'm doing z first. There's no theoretical reason to do one over the other. But so I fix z, and I'm going to plug in all the combinations of 0, 1 into xy. And that's going to give me this very nice univariate polynomial, 11z minus 4. We'll send this over to the verifier. And, if we plug in 0 for z and 1 to z, well, we're going to get 4. Sorry. I went ahead and plugged in 1 first. So yeah, plug in 0, we get -4. Plug in 1, I will get 7. -4 plus 7, 3. Cool. So that checks out. So at this step, the verifier has not found anything wrong. If for some reason the verifier computed this out and it came out to anything other than 3, the verifier stops here. Like they just go, okay, the prover's a liar. I'm done. But because it checks out, the verifier is going to go, okay, I'm going to pick some random value in my field, say R1 equals 5, and I'm going to need to compute what G1 of R1 is. So that's 51. And I'm going to send R1 over to the prover. And the prover is going to take this and go, okay, great. I know what Z should be forever now. It's 5. I'm going to fix Y. And I'm going to plug in every combination of 0, 1 to X. And that should give me 20 plus 11Y. So I get this second univariate polynomial. And the verifier receives it and checks it for 0, 1. Again, the verifier just needs to make sure that this is in fact equal to 51. If for some reason it's a number other than 51, verifier goes, you're lying, I'm done, and just quits. But since that does check out, the verifier is going to select another random value, R2, 3, R2 equal to 3, and go ahead and compute what that is for our G2. That's going to be the next value that we're going to try summing to. And that's going to now fix our Y as well. So R2 is fixes the Y. And that's going to give us this univariate polynomial when we fix those. And like I said, we just need to now just check, make sure that this is the D3. So notice that this C value that we're checking against, that's actually computed by the verifier after the first step. The first step is what the prover claimed it was, which was 3, like several slides ago. But after that point, when the verifier selects the RI, they compute the CI. So that value, the verifier knows. It's just, was that initial C correct? So that's the main thing. All right. And now the verifier finally has to make sure that this is going to be equal to the original polynomial as well. So we have what the final value is, and does it equal at this random point? Once you pick a random point, say 2. So, all right. I'm going to assume, again, if there's any questions, I would be interrupted. But I think everybody's good for the moment.
Maybe a quick question. So
yes.
Yeah, so the verifier doesn't check the GIs sent. He only checks at the end at some random value that F and G3 in this example actually hold at equal at this random point. Am I correct in that?
Yes. So the there's yes, I'm going to extend it as slightly as well. Okay, so you are correct. The original function F is only directly connected to, like, checked against the final G univariate polynomial. So we do that whole telescoping. We're just going back to the diagram. So only the final polynomial is ever checked with the original function F. Now, the verifier is implicitly checking the validity of each of these G's, not quite with F. Well, I mean, kind of with F, because we know what F evaluates to, and we know what G1 evaluates to. So what we're essentially doing in this check is going, okay, does Schwarzschild hold? So we are using Schwarzschild in each of these steps to check the GIs, but only the last univariate polynomial GV is checked against the original function F. Did that answer your question fully?
Yeah, I think so. Thanks.
Okay. And since this arithmetic checks out, the verifier celebrates and accepts the prover's claim. And like I said, there's multiple ways that you can do this. This polynomial is so short that you would just check it manually. But anyway, so the next thought is, okay, well, what about the complexities? What's going on with this? The first thing to note is that the Sumcheck protocol is perfect, satisfies perfect completeness. That's great, because that means that an honest prover will always convince a verifier. So that's wonderful. Soundness. Okay. Soundness is really the one we really care about, because that's can a malicious prover convince a verifier of a lie? There are some protocols that are, perfectly sound. But that has perfect soundness, but not all of them. So this one is going to be one of those where it's like, okay, we are bounded basically by the number of invocations of Schwartz-Zippel. So if I go back to my diagram pictorically and notice that this particular connection point probably shouldn't have existed. It probably should have been just into that CV -2, but such is life, because you don't really need a univariate polynomial GV. But ignoring that typo, we would have Schwartz-Zippel at each of these steps. That gives us V -1. And then the final evaluation is going to be another one. So that gives us V evaluations with Schwartz-Zippel. But like I said, there's a slight typo where I shouldn't have had this last step. That's a little excessive. But so the constant invocations of Schwartz-Zippel is what gives us this upper bound of our ability to deceive a verifier. Communication complexities, that's going to be based on how expensive it is to send each of those univariate polynomials to the verifier. And then the verifier's complexity is in terms of the size of my set. It's linear with respect to the size of my set and in terms of the number of variants I have. So that's not too bad. Variables I have. The little asterisks I have on soundness and verifier complexity, that's going to determine whether if the verifier is having to compute the last evaluation themselves. Because if they're computing the last evaluation themselves, it may be affected. For instance, if you use a polynomial commitment, the polynomial commitment is going to have a little bit extra soundness bound to be added to it, because you've now introduced another thing that could go wrong. But it's going to be very small, of course, but still worth mentioning. And same with the evaluation. If you made the verifier evaluate the polynomial, it's going to get a lot larger. So it shouldn't be any larger if you're using a polynomial commitment, though. So that's the complexities. I mentioned at the very beginning that you could do this with multilinear, so I figured I would add a slide and just kind of tell you how, in case that's something you've not seen very briefly. So I'm going to have a function f that is defined as my array with size v. And the multilinear extension of this is going to be this polynomial with variable x. Just I don't want to write all the x1s out, so ignore if you don't like the bold. And what that's going to be is the wth location of in my array times the quality function right here, where it's w and x. So w is my just a binary string, and x is going to be some value, a vector in my field. Now, this polynomial is very nice because if x was a binary array and x and w were the same binary array, this would just be 1. And if they were different binary arrays, it'd be 0. So what would happen is this multilinear extension produces precisely f when we're just plugging in something binary. When we're plugging in something not binary, we're going to get kind of this, like, you're going to get a number out of this. So it's going to be like, kind of a weighted sum, so to speak, of all of my array elements. And that's what multilinear extension is going to be. But because we have this nice sum, you can kind of see how you might think about Sumcheck in this instance. Certainly that's going to come into play with the protocol GKR, but that's a bit much for tacking onto one slide, to try mentioning GKR2 in depthly. But the other thing is, you might be wondering, it's okay, I have the Sumcheck protocol. This isn't a ZK call. So how do I do Sumcheck with zero knowledge? And there's a few ways to do it, but I'm going to kind of just give the quick overview of the easiest way. And that's using a random polynomial for hiding. It's from a Ben Sasson paper et al. Of course, there's a lot of big names on it, like Spooner, and I'm just not going to butcher any other names today. So it's from a 2018 paper, Ben Sasson's and Spooner on it. You find that paper, you found it. And it's going to use a random polynomial for hiding. So what's going to happen is we're in the same setup, but the prover's going to find a polynomial that's going to sum to 0 over the set that I care about. In this instance, 0, 1. And so what's happened is if I add this polynomial R of X to my F, I haven't changed the sum. It's still going to sum to C. Now you go, okay, you got to do more than just add another polynomial in there, because the prover controls the polynomial, like, and F. Okay, yeah. So what you would do is you would need to, of course, commit to your polynomial R and F to make sure you're not doing some weird black magicry. But the other thing you would do is the verifier would choose a random value row. And that's going to give us this linear combination that I can now perform Sumcheck on. So we have this polynomial, and that's what we're going to do Sumcheck on. So if the polynomial, like all the coefficients, are now given to the verifier, they're not going to be able to determine which part was R and which part was F. So that's the main thing. It's also worth, yes.
Is X here, is it the same as H before, or?
Yes. These would be like the H1s, H1, H through HV.
Okay, so it's the same set for R and F.
Yes.
Okay, perfect.
Yeah. I probably should have written H right here. I probably should have, like, at the top put, like, we're still considering the sum. But yes. We would definitely want to do Sumcheck over the same set for F and R. And this is just one of the ways to do zero knowledge Sumcheck. I believe Libra has another method. I don't quite remember that one off the top of my head. But, if you're just wanting to see that you can do zero knowledge Sumcheck, this is, quite apparent. This is also how the univariate Sumcheck has zero knowledge tacked on, which makes sense because, basically same authors of that paper. The univariate Sumcheck is introduced in Aura. It's not too complicated, but it's complicated enough that I don't think it's good to have in a general talk. But it is worth noting that the Sumcheck protocol, as described here, is only for multivariate polynomials, because we kind of have to do this multiple steps. If you just have a univariate polynomial, then you've sent me a univariate polynomial at the beginning that's F and asked me to evaluate it. So we didn't get anywhere on savings. So yeah, there is a univariate version of Sumcheck. It works a bit differently. It has some really cool properties. It's in Aura, but I didn't talk about that today because, to be honest, outside of Aura, I'm not sure where that protocol is used right off. But it's pretty cool. Anyway, so that's all. I'm happy to take more questions, but that's everything I have at the moment.
So maybe just some a basic question on maybe you mentioned it at the beginning, but why would you want to do a sum over all combinations of values of
Sure.
instead of like a subset of H, let's say?
Okay, so yes, absolutely. So the tricky part is there's a few reasons. One, the the interesting example of the Sumcheck protocol. So this is like for a moment we're going to go with the from a research standpoint the really cool motivation behind the Sumcheck protocol, and then because you asked why would I, and then I'll not selfishly answer it from an engineering standpoint. So the Sumcheck protocol paper, and this is based on memory, it actually gave a really cool way to essentially handle the principle, I believe is what it's called, the principle of a matrix. And if you remember the definition of a determinant from the really complicated definition of a determinant where it has like all the permutations and the sign of the permutation in that sum. That sign of the permutation actually makes determinants really easy in quotes to compute with nice formulas. But if you take that sign to be just only one and it's just the sum, then you actually end up with the Sumcheck protocol essentially, and the formula that you're using on the Sumcheck protocol. And that's a lot harder to compute. So you can kind of see it as a way to offload that computation. Now, from a non-theoretical math standpoint, why do we care about Sumcheck protocol? That's the real question. And that's, I would say, the most crucial reason, I would say, is GKR. GKR protocol, what it does is very abstractly is it takes your gates, your arithmetic circuit, and each layer of your arithmetic circuit is going to be represented as a single function, and you're going to do sum check over that, and that's going to allow you to essentially reduce the checking of your entire circuit evaluation to a sum check protocol essentially on each layer, and that's should be more efficient for the prover because that's going to be some constant times logarithmic computations. Are you familiar with GKR?
Yeah, I guess it will become more clear how the sum check is used if we talk about GKR and like yeah, next or
give me
later on.
give me 1 second and I will find a diagram that will also help. I don't have GKR pulled up, so I'm just going to pull up Thaler's notes or book, whatever I find real quick, because I think that will help. Like, because we can at least say enough to motivate GKR, and I'm happy to talk about it. Yes, that terrible equation. Okay,
yeah,
cool.
but we can also leave it for next time. Yeah.
Well, I figured I'll give a motivation real quick, so that people will attend. All right, GKR notes. Okay, cool. Helps if I see the notes. Okay, yeah, I shared the specific screen. And at the top, you can see that what I've been looking at for this past few days on Python. Okay, so now, very briefly, why you would, there's only so far in the weeds you can get with Sumcheck protocol, and we're going to do this very, very quickly because, as you've mentioned, we probably should dedicate a call to this potentially. But let's just kind of give people a motivation real quick on why Sumcheck protocol matters for this. And what it is that each layer, making sure I believe that it's each layer. Yeah, roughly. So each gate can be represented by this formula where we have this add, we have this multiply. And what these adds and multiplies are is basically, do we actually have an addition at this combination of gates at this layer as well? And we're going to do this if this add actually exists, then we're properly going to add those two gates together that are on this layer. And if that add if it's multiplied, we'll do a proper multiplication. Now, of course, these are all multilinear extensions, as I mentioned earlier. So you kind of see this as a weighted average. But what's happening with the Sumcheck protocol is that we're going to apply the Sumcheck protocol onto this horrible looking function. Well, this horrible looking function that takes up so much of a line that they put down here. And that's going to be kind of allows us to figure out the computation out of the gate on a particular layer. And you can go, okay, what I see happening real quickly now is that when I apply Sumcheck protocol, I get this evaluation at some gate. Cool. But now that gate is dependent on two other gates at a different layer, if I start fixing values. And I went from one Sumcheck protocol on one layer to another Sumcheck protocol, two Sumcheck protocols. And what's really cool is you can kind of use an arithmetic trick to combine them to make sure that you only have one per layer. But essentially, you're working from the output of your circuit all the way up to your inputs, where you get like one Sumcheck per layer. That's going to be the soundbite description of Sumcheck protocol for now, just because any more in depth will be probably more confusing than it's worth at this point in time, and any less in depth might be better. But hopefully that makes sense, and we can again talk about GKR later if you would like.
Perfect. Thanks.
So I guess I should add GKR to our to-do list for presentations. All right.
Yeah.
Yep. I'll let you stop the recording.
Okay.